Math Team covers a wide range of topics from geometry to pre-calculus, yet somehow, some of the hardest questions are still those of good old algebra. This video is the first part in what I hope will be a 7-part series covering every formula and theorem you need to know for Math Team. As I said in the series preview, it's my belief that Math Team should not be a test of how much you know, but rather how well you can apply your knowledge. Unfortunately, many Math Team questions do require knowledge of odd formulas that you may not have learned in your average high school math class. As a result, I've compiled a list of 14 different Math Team formulas with the timestamps given below. In each segment, I will be giving a quick summary of the formula and an example problem of Math Team difficulty. I won't be giving a detailed proof or explanations due to time constraints, however, it is my hope that through the example problems, you will learn the key words and key situations that should set off a trigger and make you think to use each formula. At this point, it's on to our first formula. The binomial theorem is a useful trick for expanding polynomials. It says that x plus y to the nth power is equal to the summation of n choose k times x to the n minus k times y to the k, where n choose k is equal to n factorial divided by k factorial times n minus k factorial. Let's look at the example x plus 1 cubed. We can write out this nasty equation, however it all simplifies to the fairly nice expression x cubed plus 3x squared plus 3x plus 1. For this particular question, we are given x plus 1/6 to the 9th power. Using the binomial theorem, we can expand it. Now, when looking at any question that has a series like this, I like to write out the first few terms to find a pattern. For this particular question, we are looking for integer coefficients. In this case, 9 choose n must be a multiple of 6 to the nth power in order for the coefficient to be integral. We can see that this is true for 9 choose 0 and 6 to the 0th power. Therefore, n equals 9 is one of the solutions. In the second term, we have 6 on the bottom, but no even numbers on top, so that clearly fails. At the third term, we have 9 times 8, which is equal to 6 times 6 times 2, and the bottom is 6 squared, so this will have an integer coefficient. That means that m is equal to 7. Now, just as a quick check, we can see that as we move to the right, looking at more and more terms, the top won't have enough multiples of 3's and 2's to match the multiples of 6's on the bottom. At this point, it's safe to say that there are no more integral coefficients. But as an aside, if a Math Team question says that there are 2 solutions, you don't really need to finish the problem once you found both solutions. Anyways, we get that n is equal to 9 and m is equal to 7, and 9 plus 7 gives us our final answer, which is 16. The Cauchy-Schwarz Inequality tells us that the sum of squares times another sum of squares is always greater than or equal. I'm just going to write out the formula. The power of the Cauchy-Schwarz is that there will always be a set of points that causes the two sides to be equal to each other, and that makes this useful for finding minimums and maximums. For this particular question, we are being asked for the minimum of this expression. This is a really hard question because it's not terribly obvious how to go about solving it. We can plug in numbers to make an educated guess, but proving a minimum can be really difficult. When the answer isn't completely clear for a question like this, it's never a bad idea to first expand our terms. One way to get rid of the variables is to multiply each term by its inverse. When we look at this, we can quickly realize that the inverses are just rearrangements of our original terms. Now this is where the Cauchy-Schwarz should pop into mind. We get that the left side is greater than 6 squared. We have one issue though. Here we have a over c squared, b over c squared, b over a squared, and so forth. And we don't want that. We don't want all these squares. We want our original expression on the left side so that we can find its minimum. Now to remedy this, let's play around and replace everything with a bunch of square roots. And this is actually really helpful. The reason this inequality worked in the first place is because, for example, a over c times c over a is 1. But similarly, the square root of a over c times the square root of c over a is also 1. So replacing everything with a bunch of square roots has no effect on the right side of the equation. The right side is still 6 squared. Then with some simple algebra, we can get that the left side is our original function squared. And all variables are positive, so we can then take the positive square root of both sides, and we then get that our original function is greater than or equal to 6. So our minimum is 6. Assume we have some polynomial ax to the n, bx to the n minus 1, cx to the n minus 2, and so forth, where all the coefficients, a, b, and c, are all integers. If we know that one root is a plus the square root of b, the conjugate root theorem says that another root must be a minus the square root of b. Similarly, if one root is a plus bi, another root must be a minus bi. Again, this is when we know that all the coefficients are all integers. Another way of writing polynomials is a times x minus x1 times x minus x2 and so forth, where x1, x2, x3, and x4 are all roots. In this particular question, the coefficient of the highest order, that is x to the fourth, is 1. Therefore, a must also be 1. We know that the square root of 2 plus the square root of 5 is one root. According to the conjugate root theorem, one root must also be the square root of 2 minus the square root of 5. But because there are two square roots here, another root could also be the negative square root of 2 plus the square root of 5. And then similarly, negative square root of 2 minus the square root of 5 is a conjugate to both of those other roots. In other words, the conjugate root theorem says that all four of these are solutions. We can plug in the square root of 2 plus the square root of 5 because it was given. Then we can choose one of its conjugates. Some factoring gives us x squared minus 2 root 2x minus 3. With some cheating, we can use the same trick that we use when we use the difference of squares. If we want to rationalize the middle term, we can flip its sign. Then, when we expand this, all the square roots will disappear. This leaves us with x to the fourth power minus 14x squared plus 9. Lastly, we can't forget to format our answer. A plus b plus c plus d is 0 minus 14 plus 0 plus 9, which gives us a final answer, and that is negative 5. I really don't like the Descartes rule of signs. Now, no shade on René Descartes, he's one of my favorites. However, this particular equation is one of those formulas that's fairly useless, but it will randomly pop up on tests, so you need to know it. The rule of signs says that the number of positive solutions to a function is equal to the number of changes in sign minus some even number. If we take f of negative x, the equation flips, so the number of sign changes in f of negative x is the number of negative solutions minus some even number. In this example problem, there are 5 sign changes. It starts with a positive x to the 8th, then a negative x to the 6th, and a positive x to the 5th, and so forth. If we plug in negative x, we see that there are only 3 sign changes. This means that there must be 5, 3, or 1 positive solutions. Again, 5 sign changes minus some even number, 5, 3, 1. And there also must be 3 or 1 negative solutions. Again, it's the number of sign changes minus some even integer. Now, because there are multiple solutions, this formula isn't very accurate and isn't very applicable. Now, this question is the odd case where the rule of signs does help. There is only one sign change in f of x. Because there are no other possible solutions, we know for a fact that there is one and only one positive solution. Then f of negative x also has one sign change, so there must be one and only one negative solution. By the fundamental theorem of algebra, this equation must have 21 not necessarily distinguishable solutions. The last option is the 0 case. 0 is neither positive nor negative, so it must be checked individually. In this case, 0 accounts for only one root. If there are a total of 21 roots, 1 positive, 1 negative, 1 0, there must be 18 imaginary solutions. There are 3 logarithmic identities. The first is the log of a to the b power is b times the log of a. The second is the log of a plus the log of b is equal to the log of ab. And the third is the log of a in base b is the log of a over the log of b. Whenever you see a variable in an exponent, you should expect logs to play a role. And when logs are playing a role, one of these identities is probably just around the corner. For this particular question, we are given a function with a limited range. We are given a limited domain for x, that is, x is between 0 and 2014. And this question is asking for the total length of all intervals. On the surface, that's a mouthful. So let's draw a picture. Let's draw f of x and a line at y equals 1. We see that between each integer, there is only a sliver of a space where f of x is less than 1. The interval is going to be the set of x values where f of x is less than 1. It is the domain of the x values where this is true. Now that we know what the question is asking, we need to come up with a formula for it. My first instinct is to write out the function for f of x and to set it as less than 1. The floor of x is the same thing as rounding down, and that means that the floor of x will always be an integer. Integers are much easier to work with than rational numbers, so we may want to solve for x in terms of the floor of x. There's another big clue that may inspire you to do this. When the question says total length, it wants the sum of all intervals, and the sum may make you think of summations. Summations are easy to work with, but we need an equation that's in terms of integers only. With some algebra, we get this expression. To solve for an exponent, we can use a logarithm. And voila! We just found the upper bound for x. But what's the lower bound? It may be helpful to go back and look at the graph. Here we see that each interval starts at an integer and ends somewhere before the next integer. Now this may be obvious, but x is always greater than or equal to the floor of x. Again, the floor of x is x rounded down, so by definition, x will always be greater than or equal to the floor of x. To get the length of each interval, we can subtract the lower bound from the upper bound. This gives us an equation for each interval between two integers. If we're going to sum up all the intervals together, we're going to have to sum this equation for all values of the floor of x. The floor of x is by definition an integer, so we can replace it with an integer called k. 1 over k plus 1 is the same as 1 plus k over k. If we write out the first couple of terms, the patterns should start to pop. And when you see logarithms, the logarithm identities should spring into your mind. We can simplify this into the logarithm of one giant product, and then, with some satisfying crossing out, we can simplify it all to this one equation. And lastly, the log base 2014 of 2014 will be 1. We can prove that using the third identity that we learned. Newton's sums is a set of equations for finding the sum of roots, the sum of squares of roots, the sum of cubes of roots, and so forth. The formulas are admittedly very complicated and quite difficult to remember, but it's well worth your time to commit these to memory. Lots of math team questions like to ask the sum of the squares of your answers, so again, Newton's sums will come quite in handy. Let's say that we have some polynomial of the nth order with coefficients a sub n minus 1, and a sub n minus 2, etc. We'll define s1 as the sum of all roots to the first power. We'll define s2 as the sum of all roots to the second power, s3 all to the third power, and so forth. According to Newton's sums, this pattern of equations will always hold true. Again, the pattern I just displayed is quite complicated and overwhelming, so this is something you'll have to be intentional about memorizing. Hopefully this example problem clears things up. Here we have a cubic function. it wants you to find the roots, which is already hard to do by hand with a cubic equation. Now this particular equation is even harder to solve because not only are the roots not real, but they have irrational components. In other words, this equation is messy. Now, the question is asking for the sum of the cubes of the roots, and as a result, we can avoid all that imaginary irrational junk by simply using Newton's sums. First, we need to solve for the sum of the roots. The first coefficient is 1 and the second is -2. With some algebra, we get that the sum of the roots is just 2. Onto the sum of the squares. We can plug in 1, -2, and 6. We solved for S1 and saw that it equals 2. When we plug that in, we get that S2 is equal to -8. And lastly, the sum of the cubes of the roots. This time we're inserting all 4 coefficients. We're replacing S2 with -8 and replacing S1 with 2 again. Add up all the numbers and you'll find that the sum of the cubes of the roots is -58. The purpose of a partial fraction decomposition is to break apart the denominator of a fraction with a polynomial on the top and on the bottom. I wrote out a formula, but it doesn't mean much without context, so we're going to jump right into the example problem. In this example, we have 2 series being added together. Your first instinct may be finding a common denominator and adding the fractions together. However, this results in a big summation that you probably couldn't figure out with just a pen and paper. So let's look at an alternate solution. When you're trying to add a bunch of terms together to get things to cross out, you want to make it as simple as possible. We see that the denominator in b's summation is n squared plus n, and that can be factored into n and n plus 1. Here's the trick to partial fraction decomposition. We multiply everything by the original denominator. We then choose a value of n that causes p to disappear. In this case, p disappears when n equals 0 because 0 times p is 0. We then solve for q. Next, we choose a value of n that causes q to disappear, and in this case, -1 causes the coefficient of q to be 0. We then solve for p, and what we now have is 2 separate terms. The finish line is already in sight. Because 1 over n is equal to a, we can just replace 1 over n with a. Now for 1 over n plus 1, we should look at its series. 1 over n plus 1 is 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. And this is the same as a, except a's first term is 1 divided by 1. So therefore 1 over n plus 1 is just a minus 1. Now lastly, we solve for b in terms of a, and then we solve for a plus b, and as a result, we get that a plus b is 3. Every mathematician seems to know the Pythagorean theorem. For a right triangle, a squared plus b squared equals c squared, where c is the hypotenuse. You probably know some of these triples. We have 3, 4, 5, 5, 12, 13, or 8, 15, 17, to name a few. We call these Pythagorean triples. Now these numbers may seem random at first, but, believe it or not, there is a pattern and we can write out a formula for these triples. For any triple, a is equal to x squared minus y squared, b is equal to 2xy, and c is equal to x squared plus y squared. Because each side is positive, x must be greater than y. Now if you plug in these equations, proving that a squared plus b squared is equal to c squared is fairly straightforward. Now ultimately, these equations hold true for any value of x and y, but it's especially helpful for finding triples with integer values. The following example will illustrate why. For this example, we're given the perimeter of a right triangle. At first, you may be inclined to write out the equations a squared plus b squared equals c squared, and a plus b plus c is equal to the perimeter, which in this case is 1748. But this is messy, and it provides no intuitive way of solving for integral side lengths. When you're in this situation, using the Pythagorean triples theorem is a good way to go. By replacing a, b, and c with x's and y's, we get that the perimeter is equal to 2x squared plus 2xy. Dividing everything by 2 gives us that 874 is equal to x squared plus xy. As a side note, the most important aspect of integers is that they have factors. By definition, an integer is the product of other integers. In this case, we get to factor out x and get that 874 is equal to x times x plus y. Since x, y, and 874 are all integers, x and x plus y must both be factors of 874. With some guesswork or a calculator, we can factor 874 into 2, 19, and 23. Because x must be greater than y, we should set x equal to the greatest factor, in this case 23. That means that x plus y is 2 times 19, which is 38. This gives us x equals 23 and y equals 15. From here, we can use the theorem one last time. If c is the hypotenuse and c equals x squared plus y squared, the hypotenuse must be 15 squared plus 23 squared, which is 754. I love the simplicity of the remainder theorem. If we divide some polynomial by x minus a, we get the quotient plus a remainder divided by x minus a. It's the same principle as normal division. If we divide 9 by 7, the quotient is 1 and the remainder is 2, so 9 over 7 is 1 plus 2 over 7. If we multiply everything by x minus a, we can write p of x as q of x times x minus a plus r. The remainder theorem says that the remainder is p of a. In this question, we're given a quotient and a remainder, which should immediately inspire you to write p of x in this form. We're then told that q of x is divided by x plus 16 with a remainder of 24. Let's call its quotient little q. Then lastly, we have p of x divided by x plus 16. Let's call its quotient q1 and its remainder r. The question is asking for r. Now solving for a remainder should immediately make you think of the remainder theorem. The remainder theorem tells us that r is p of negative 16. Let's use our other equation to solve for p of negative 16. This results in q of negative 16 times negative 16 minus 20 plus 10. We now have to solve for q of negative 16. Because negative 16 is the a value for this equation, we can use the remainder theorem again. Q of negative 16 is equal to its remainder, which we're told is 24. Let's replace q of negative 16 with 24. Then lastly, we compute the string and get that p of negative 16 is negative 854, which we previously showed was the remainder. The RMS-AM-GM-HM inequality gives us a relationship between 4 different types of averages. We have the root mean square, arithmetic mean, geometric mean, and harmonic mean, and ultimately you don't need to know what each one means. What you do need to know is the relationship between the 4. What makes this so powerful is that the RMS is always greater than AM, which is always greater than GM, which is always greater than HM. Always except when A is equal to B. When A is equal to B, all 4 of these expressions are equal to each other. This fact is useful for finding minimums and maximums. In this question, we're trying to minimize an expression. For any math team question with an expression, you should start by assigning it a variable. This makes it easier to manipulate the expression. Let's call this expression A. At this point, I'm guessing there's no obvious solution popping out. When this happens, it's never a bad idea to play around with our equation. In fact, expanding it is always a good idea when you're stuck. Let's now get a common denominator. We now have a new problem. X times y appears 5 times, but x and y each appear individually in the numerator. It's at this point that we should maybe reread the question for some insight. In doing so, you may realize that we're given x plus y, and we can get x plus y down below by factoring out a 3. Let's replace that with 6, and then let's simplify. At this point, we've vastly simplified our original expression. It should now be obvious that x times y is integral to this question. Like any math team question, there has to be a trick. Here, the trick is noticing that we have x times y and we have x plus y, which should make you think of the RMS-AM-GM-HM inequality. In particular, you should be thinking of the AM-GM portion, which states that x plus y halves is always greater than the square root of xy, unless x and y are both equal. We know that x plus y is 6, and we know that 6 halves is 3, and that 3 squared is 9. Let's now solve for xy up top. Then by the transitive property, 27 over a minus 1 is less than or equal to 9. We can then multiply both sides by a minus 1, and lastly, we can solve for a. Because we use the AM-GM inequality, we know that there is some set of numbers that makes a not just greater than 4, but equal to 4, and that makes 4 that expression's minimum. As the name suggests, Simon's favorite factoring trick isn't a formula as much as it is a technique, or a trick. One time I had a math teacher tell me that I could not factor or simplify xy plus x plus y. That's embarrassing. To factor this, we first need to pull out an x. We need to add 1 and subtract 1. This has the same effect as adding 0, so it doesn't change anything. We then factor out a 1, and this may seem silly, but it's important because we're now going to factor out the y plus 1, which leaves us with x plus 1. Ultimately, our original expression gets factored out to y plus 1 times x plus 1 minus 1. For this question, we're told that the difference between the sum and the product of x and y is 222. Whenever a math team question asks for ordered pairs that are integers, there are 2 ways to approach it. The first approach is to solve for one variable and to find a pattern. This works well for linear equations. Now, in my opinion, the better approach is to arrange your equation into a product of a form of x and a form of y, and this allows us to view the factors. That explanation was clunky, but it'll make more sense later. Long story short, we want to break apart x and y. Let's distribute the negative sign. We can use Simon's favorite factoring trick to factor x and y. Pull out the x, add and subtract 1, factor out y minus 1, add 1 to both sides. We now have x minus 1 times y minus 1 is 223. It's easy to check that 223 is prime. That means that 223 is 223 times 1, or negative 223 times negative 1. And this means that x minus 1 can be 1, and y minus 1 can be 223. Then we have the reverse. And lastly, we have x minus 1 is negative 1, y minus 1 is negative 223, and we have that reverse. That means that there are only 4 ordered pairs that fit this equation. Synthetic division is a way for finding the quotients and remainders when you divide a polynomial by x minus a. There's no real formula for synthetic division, so let's just jump right in. With this question, the tricky part is that we're dividing 2x plus 7 and that we can't use synthetic division if x has a coefficient. So let's do a little bit of tricky math manipulation. If we multiply the top and the bottom by 1/2, we can get rid of the coefficient. I don't want fractions on top, so let's pull out the 1/2. According to our original equation, this is equal to q of x plus k over 2x plus 7. Let's multiply both sides by 2. And let's divide the top and the bottom of the rightmost term by 2. What we've now shown is that dividing f of x by x plus 7/2 will result in double the quotient portion, but the remainder will be the same as when we divide f of x by 2x plus 7. We're going to solve for x, which gives us negative 7/2. We'll now write out the coefficients of f of x. We'll drop the first coefficient, multiply it by negative 7/2. That gives us negative 7. We'll add negative 7 to 21, which gives us 14, and then we'll multiply 14 by negative 7/2, which yields negative 49. 35 minus 49 is negative 14, and we'll repeat this pattern until it's completely filled out. The first 4 numbers are the coefficients for the quotient portion. However, it's going to be double the real q of x because x has a coefficient of 2. We get 4 as the remainder portion. Remember, this is not double, which is what we proved earlier. Therefore, 4 is the remainder and the answer to this question. Vieta's formulas are a series of relationships between the roots of a polynomial and its coefficients. Let's first look at the quadratic formula, which is the most straightforward example of this. The sum of its roots is negative b over a, and the product of its roots is c over a. There's a quick intuition behind this. If we write p of x as a times x minus root 1 times x minus root 2, we can expand out all of the terms. If we pull out negative ax, the second term has a coefficient that's negative a times the sum of the roots, and the third term has a coefficient that's a times the product of the roots. If we go more general, we can see that the sum of the roots is always negative a sub n minus 1 over an. If we then sum every possible pair of roots, we get a positive a sub n minus 2 over a sub n. This has to do with the fact that we subtract the roots. If we multiply two negatives, it becomes positive, and that causes Vieta's formulas to alternate in signs. If this pattern continues, the next will have the sum of every possible triplet, the following the sum of every possible quadruplet, and so forth. The last term will be the product of all n roots. This will equal negative 1 to the n times a naught over an. For this question, p of x has one real solution and two imaginary solutions. You don't want to have to solve this, and thankfully the question isn't looking for each root. It's not looking for you to solve it. What the question is looking for is the product of each root plus 3. Because we have a product of the roots, we should start considering Vieta's formulas. Let's expand a plus 3b plus 3c plus 3. We get abc plus 3 times ab plus bc plus ca plus 9 times a plus b plus c plus 27. The sum of the roots, which is a plus b plus c, is negative b over a, and that's 11 over 3. The sum of the pairs of the roots is c over a, which is 83 over 3, and the product of the roots is negative d over a, which is negative 29 over 3. If we plug in those values, we get that the answer is 400 divided by 3. Finally, we made it through all 13. To anyone who stuck around through each and every segment, I applaud your commitment. Now that I've covered the algebra formulas, geometry is next up on the list. I've already started that video, but the sheer number of formulas is near double the amount of the algebra formulas, so it may take a while to come out. Anyways, thank you again. If someone comes away from this video learning a formula they never knew before, that in itself is a huge success. To all the high schoolers, make sure you commit each and every one of these to memory, so that on your next math team test, you can whip out a formula and make your day a whole lot easier.